All right, we've been discussing whether we can tell certain processes, such as, we'll just say, the boiling of water, is a favored process or not. And I've mentioned how the change in enthalpy or the change in entropy of the system can help us determine whether the process will be spontaneous or not. And we know that processes with delta H negative, those tend to be favored, and processes with delta H positive, those tend to be disfavored. We've talked a lot about enthalpy before, and so I'm not going to cover this much further. We are going to look today at the entropy. In this case, we know that processes with delta S positive are favored, and processes with delta S negative are not favored. And I want to go over entropy a little bit more to give you a bit of intuition of what's going on with the entropy. I've mentioned how we can look at the entropy as probability of matter. So if we imagine, we'll just take a sheet here and another sheet, and we're going to imagine that I'm going to just throw a bunch of particles onto this sheet and a bunch of particles onto this sheet. We'll say x's represent particles, and in one case the system of particles that I throw onto the sheet looks like this. In the other case, they line up like that. Which case is more probable? Well, of course, this is the case that's going to be more probable. And in this case, it's going to be less probable that if I randomly throw particles onto a sheet, they're going to line up like this. So this is sort of the way we want to think about entropy and changes in entropy in terms of matter. What actually is happening with the matter? Is the matter tending to go to a more probable state, or is the matter is the matter going to a less probable state? And this helps us understand that as we go from a solid to a liquid to a gas, that's similar to going in this direction. So the process of going to a solid to a liquid to a gas, that represents an increase in entropy, so delta S positive. But if we go from a gas to a liquid to a solid, that's akin to heading in this direction in terms of matter, and so in that case we have delta S is negative. There's an important law of thermodynamics that deals with the entropy. It is known as the third law of thermodynamics. It's a pure crystal at 0 Kelvin has 0 entropy. This tells us a couple things. The entropy of a substance increases with temperature. So for example, if I have a gas, we'll just say a gas at 100 Kelvin, so it could be oxygen gas, versus a gas, the same gas, at 1000 Kelvin, this gas is going to have a higher entropy than this one. So entropy scales, so to speak, with temperature. The motion, the ability of the particles at the higher temperature to be mixed up is much greater at a higher temperature than it is at a lower temperature. All right, let's just do a couple examples here. Let's compare, say, these three substances. So solid sodium chloride, gaseous sodium chloride, and aqueous sodium chloride. Between these three substances, which would we expect to have the lowest entropy? Well, I hope you see that crystalline solid sodium chloride is going to have the lowest entropy. And, well, this is a little tough for you to figure out. We know that these would have higher entropy. You might guess that aqueous sodium chloride is going to have a lower entropy than gaseous sodium chloride, because this would be in the liquid type state, But we'd have to remember here, we'd have a mixture. We'd have a mixture of both water and sodium chloride, so there'd be some mixing that would occur, and in that case, this may be higher than this. But nevertheless, I'm not too worried about that, as long as you understand that solid sodium chloride would have lower entropy than either of these two. You have good intuition for what I want you to look at. How about these two here? H2O gas versus H2S gas. So here we have two substances that are in the same phase, but one of them's bigger than another. That's interesting. Which of these two substances, which I can write like this, would have the higher entropy? That seems kind of tough, doesn't it? Well, it turns out that the larger the molecule, the larger the substance that makes up, the larger the molecule that makes up a substance, the higher the entropy it's going to have. So because sulfur is larger than oxygen, H2S gas, if given the same amounts at the same temperature, H2S gas is going to tend to have a higher entropy than H2O gas. And that's because, if you just want to think about it, there's more electrons in H2S than there is in H2O. And because there's more particles, you have a better ability to mix everything up. Let's look at C2H4 gas, which has a molar mass of 28 grams per mole, if you look it up. And over here we have N2 gas, also 28 grams per mole. Here they're the same size in terms of mass, but let me just draw it out this way. Here's the Lewis structure for each particular substance versus this. In which case would you expect the electrons in the substance to have more freedom of motion and therefore have more ability to spread out? I hope you see this one here. And so it does turn out that C2H4 gas has a higher entropy than N2 gas. And then finally, we'll go over one more case. We'll look at liquid sulfuric acid and gaseous sulfuric acid. That should make sense, that this is going to have the higher entropy. Now we've already recognized that processes with delta S positive, these are favored, matter spreads out. And delta S negative, this is disfavored, matter tends to concentrate. Now I want to look at some actual values of entropy for some particular substances. And I'm happen to be on chapter 19, PowerPoint slide 11 right now. I'm looking at a chart there. And I'd like you to first compare the values for the standard entropy of water, gaseous water and liquid water. So let's look at these. Gaseous water, if I look at the chart, is 188.84 units are joules per mole per Kelvin. And liquid water is 69.95 joules per mole per Kelvin. That makes sense. The gaseous form of water has a higher entropy than the liquid form of water. And we can actually calculate delta S now for this process. H2O gas going to H2O liquid. Very easy to do. If I've got 1 mole of this stuff here, that's about 70 joules per mole per Kelvin. And that's about 189 joule per mole per Kelvin. I can find the entropy change. This is going to be the final entropy minus the initial entropy, right? So what is my final entropy. Well, that's 70 with the units. I'm not going to write them in. Minus 189. 70 minus 189. That comes out to minus 119 joules per mole per Kelvin. I've just calculated the delta S, the change in entropy for the process of gaseous water condensing to liquid water. It's going to be minus 119 joules per mole per Kelvin. Now let's compare the entropies of these particular substances. Let's see, gaseous methane, gaseous ethane, and gaseous propane. Should the entropies increase as we go this way or decrease as we go this way from methane to ethane to propane? Let's look up the values. These are all units of joules per mole per Kelvin. Well, it looks like methane is 186 roughly joules per mole Kelvin. Ethane is 229 and propane is 270. So we see as the molecules get larger, the entropy increases. All right, let's look at the next one. Explain the trend in standard entropy. Let's see, Cl2 gas versus Br2 liquid versus iodine solid. Let's look at those standard entropies. So if I look on the chart, I can see Cl2 gas is 223. These are all, again, units of joules per mole per Kelvin. This is 152, and this is 116. Oh, wait a minute. This is getting bigger as I go from here to here. Why is the entropy dropping? Oh, because if I look at the states, I see that the state of matter really significantly drives the entropy, much more so than how large the substance is. And that should make sense, right? I mean, if I've got gaseous chlorine, I'm going to draw dots as representative of the particles. It's going to look something like that. If I have liquid bromine, those particles are going to be a little bit more organized. And if I have solid iodine, those particles are going to be really organized in a solid. All right, we're going to now calculate the standard entropy change for 2H2 plus O2 gas going to 2 moles of water. Now let's think about this. Before I do the actual numerical calculation, I want to actually think about what's going on. If I look over here on this side of the equation, notice I have 3 moles of a gas. So 3 moles of a gas are going to 2 moles of a gas. So if I've got, let's just imagine it this way, 3 moles of a gas that are somehow combining such that at the end I only have 2 moles. Notice that I've concentrated matter. I've made it less available for the matter to spread out. Here it can spread out in 3 particles. Here it could only spread out in 2. So we see that in processes where the number of moles of a gas decrease, that should show a decrease in entropy. So I'm going to expect delta S to be negative for this particular process. Let's figure out what it actually is. So I'm going to look up the standard entropy for gaseous water, and it's about positive. They're all positive for entropy, 189 times 2 of them. And then for oxygen gas, it looks like it's 205. Again, these are all units of joules per mole per Kelvin. And I'm going to look up hydrogen gas, and that's about 131. And there are 2 of those. And the delta S is going to be the entropy that we end up with, so that's the the product, so that's all this over here, minus the entropy that we start out with, which is going to be my reactants. So let's see. times 189, that's 378, minus 2 times 131, that's 262, and 205. 262 plus 205 is 467. I need to subtract 467 from 378, so I'm just going to make it negative and add 378. And as expected, the change in entropy for this process is negative 89, and the units of entropy are joules per mole per Kelvin. So because I went from 3 moles of a gas to 2 moles of a gas, I would expect an entropy drop, which is exactly what I saw. All right, now let's look at this. 2H2 gas plus O2 gas going to 2H2O liquid. Is this going to be favored under standard conditions? Well, in terms of the entropy, I've got gas going to liquid. So that means my entropy change is going to be negative, which is disfavored. So in terms of the entropy, this is not a favored process, but that's only half the story. We also have to consider delta H. And you might remember that I have done this reaction before. I take hydrogen gas and I react it with oxygen gas. Remember, I put this in a balloon, and then the oxygen gas from the air reacts with it explosively, and it releases a ton of energy. So this is highly exothermic, which is favored. Remember, exothermic processes, they release energy to the surroundings, and that gets spread out all over the surroundings. So in this particular case, where the signs are the same, one process ends up disfavoring the overall reaction while the other one favors it. So in this case, we don't really know. It depends on temperature. And in the next lecture, we're going to talk a little bit more about how we can determine whether a process that's favored in one case and disfavored in another, how we determine which way it's going to go based on temperature.